The title of my talk for you today is Inflation, the Bang in Big Bang. Inflation, what is it? So inflation is this thing that most cosmologists believe happened right at the start of our universe. And we think that it's basically responsible for all of the large-scale structure that we see around us today. So that's galaxies and groups and clusters of galaxies. And we think it lasted for this absolutely tiny fraction of a second. We think that it lasted for about a millionth of a billionth of a billionth of a billionth of a second, which is a very short period of time. So before we get into the nitty-gritty of exactly what this inflation is, first I think it's quite fun if we try and get a grasp of how short a period of time that is, how quickly inflation took to happen. So to begin with, I'd like some audience participation. I'd like you all to clap along with me, and we're going to clap around about 1 clap per second, okay? So, excellent. There's about a second in between our claps right now. So I'd like you all to now please clap twice as fast. There we go. So there's roughly half a second in between our claps. On the count of 3, I'd like you all to clap as quickly as you possibly can. There you go. Clap fast. Woo! Fantastic. Everybody stop. So I hope we'll all agree we're probably clapping quite quickly, and the period of time in between our claps was probably quite short. Well, this guy, Brian, he is officially the world's fastest clapper. And he can clap around about 802 times in 1 minute, which works out at about 7/100ths of a second in between his claps. So he's clapping very quickly, much faster than us, probably. Something I think is quite cool is that when things happen really quickly, we tend to say that they happen in the blink of an eye. Well, a blink of an eye lasts a few tenths of a second. So this guy's clapping faster than you can blink. So that's fairly nifty. So that's tenths of a second. Hundredths of a second is about how fast anyone can clap. Here we go. Let's go faster. There you go. So that camera flash, that lasted about 1,000th of a second. So that's 10 times faster than that Brian can clap. So let's go faster still. Let's go 1,000 times faster. Let's get to a millionth of a second. So bankers in London, at the London Stock Exchange, they can buy and sell shares millions of times a second. So that's really fast. Let's go faster still. Let's go to a billionth of a second. So that's 1,000 times faster again. A billionth of a second is such a short period of time that in it, light can only travel 30 centimeters. Light can get from about here to here in a billionth of a second. So we're getting really quick now. So surely, on such short time scales, nothing interesting can happen. Well, interesting stuff does happen. So let's go to the middle of a nuclear power reactor, because nuclear power reactors are cool. And in the middle of nuclear power reactors, you have big, heavy uranium atoms just sort of sat there, and little tiny neutrons zipping around. And a little tiny neutron, every now and then, will crash into one of the uranium atoms. And the uranium atom will split apart, throw out more neutrons. Those neutrons will go on, hit more uranium atoms, which split apart, so on and so forth. That is a nuclear chain reaction. It's the power in nuclear power reactor. And each step in that nuclear chain reaction lasts about 10 billionths of a second. So cool stuff is happening really quickly. But we need to get even faster. Let's go to 1/1,000,000th of 1 billionth of a second. So that's 1,000,000 times faster. We call a millionth of a billionth of a second a femtosecond, because it's difficult to keep saying millionth of a billionth. So you can read this slide. You can see, because of chemical reactions at the back of your eye, which last just 200 femtoseconds, or thereabouts. So there's really fast stuff going on right at the back of your eye, which enables you to see. But again, that's still not fast enough. Let's go faster. Let's go to a billionth of a second. So that's 1,000 times faster again. So we call a billionth of a second an attosecond, because a billionth of a billionth is difficult to say. And 20 attoseconds, or slightly less than that, is the shortest interval of time that we have yet been able to measure. So we are now getting to the limits of how quickly we can time things. So that's an attosecond is roughly how long it takes electrons to move around inside atoms. So if you remember back to a billionth of a second, light could travel 30 centimeters. In a billionth of a second, light can travel about the length of 3 hydrogen atoms. So this is really short period of time, but still not fast enough. So let's go 1,000,000 times faster again. Let's go to 1/1,000,000th of 1 billionth of a second. So I want to transport you all now from where we are here to Geneva, to CERN, the Large Hadron Collider. They're firing particles round in these massive circles, hitting them together, and particle interactions are taking place. Those particle interactions last really short periods of time, and some of them last just a few millionths of a billionth of a second. So this is like as fast as we can get to down on the Earth. That's sort of it. That's the fastest stuff we can do. And that's still not how short a period of time inflation took to happen. We need to go 1 billion times faster again. So we are now down to 1 millionth of 1 billionth of 1 billionth of 1 billionth of a second. And that's really difficult to say. And it's such a short period of time that we don't really know of anything else that happens there. So there's not an easy way to say it. There's not like a nice name for a millionth of a billionth of a billionth of a billionth of a second. So you just have to put up with me saying that over and over again. So this is how short period of time we think inflation took to happen. Let's now try and delve into the nitty-gritty of what this inflation might be. So to do that, we have a diagram. That on the right-hand side, this is us over here. Those blobs of light, they are other galaxies. And if we go back in time, around about 14 billion years, that's the Big Bang. That is the start of our universe. I want you to ignore all the labels other than that one, which says inflation. So inflation is the first thing that happened in the history of our universe. Right after the Big Bang, inflation kicked in. And it lasted for this tiny fraction of a second, and the universe expanded faster than the speed of light. So let me say that again. Inflation is this thing that most cosmologists think happened right at the start of our universe. And we think that for a tiny fraction of a second, the universe expanded faster than the speed of light. And that's responsible for all the large-scale structure we see around us. That makes a lot of people sit very uncomfortably because surely nothing can travel faster than the speed of light. We're always being told nothing can go faster than the speed of light. So physicists have a sort of get-out-of-jail-free card, if you like, for this one. What we say is that no particle can travel faster than the speed of light, but the very fabric of reality, space-time itself, that has no speed limit. A way to think about it, if you like, is that you could put me in a swimming pool and I could swim at about 2 meters a second, okay? If you then pick me up out the swimming pool and drop me in a river, and the river's flowing at 10 meters a second and I can swim at 2, I could be traveling at 12 meters a second, even though I'm physically not swimming any faster than 2. So that's a way you can think about it if you like. So excellent. The universe expanded faster than the speed of light for a very tiny fraction of a second. How is that responsible for anything, let alone galaxies and massive clusters of them? So to try and answer that, I've drawn a diagram. This is a representation of what our universe might have looked like before inflation. So in the first moments of creation, our universe could look something like that. It would have been much smaller than that. It would have been trillions of times smaller than a proton. So protons are things that make up atoms. Atoms are made of protons, neutrons, and electrons. The universe at this point was trillions of times smaller than a proton and trillions of times smaller than an atom. So it was absolutely tiny. And what you notice is it has that sort of ripples. Some bits are slightly brighter, some bits are slightly darker. Well, they're called quantum fluctuations. Don't worry about the technical name. Basically, on the smallest of distances, our universe is inherently random. It's sort of foamy and frothy, and sometimes things bubble up and particles pop into existence, and some bits are slightly more energetic and some bits are slightly less energetic. So that's a very early universe. Inflation kicks in, and for that tiny fraction of a second, the universe expands faster than the speed of light. And it balloons from something much smaller than a proton to about the size of a grapefruit, or to be specific, a pink grapefruit. So that's our universe. Just after inflation, you could hold it in your hands. It kind of looks a bit pathetic, doesn't it? But that is the bang in Big Bang. Our universe ballooned from something trillions of times smaller than a proton to about the size of a pink grapefruit. And what about those quantum fluctuations? What about that inherent randomness of the universe? Some bits bubbling up and being slightly more energetic. Well, they got stretched out too. So inflation stretched out the inherent randomness of our universe, little bits that were slightly warmer, little bits that were slightly cooler. And so some bits of my pink grapefruit universe are slightly more dense, and other bits of my pink grapefruit universe are slightly less dense than others. So they are the seeds that will later go on to become galaxies and clusters of galaxies. So what happens is if you fast forward, say, a few billion years, those overdensities through gravity drag more bits of matter in, and that matter collapses together and makes galaxies and clusters of galaxies and stars and planets and cows and sheep and you and me. Fundamentally, we are all here because of something that happened right at the start of our universe, where for a tiny, whiny fraction of a second, a millionth of a billionth of a billionth of a billionth of a second, our universe expanded faster than the speed of light. And it dragged out the inherent randomness of our universe and turned them into seeds, seeds that later went on to be all of us. So we're here thanks to something that lasted for shorter, quicker than bankers can buy and sell shares on the stock market, quicker than any of you can clap your hands, faster than you can blink your eyes. Thank you for listening.